Everyone. I would like to begin this presentation with an analogy. As we all know, some plants thrive in direct sunlight, while others need shade. Some prefer dry soil, while others requires moist environments. So each plant grows best when it gets its unique combination of light, water, nutrients, and temperature conditions. Plants need different amounts of sunlight, water, nutrients to thrive. Tasks in multitask learning also have unique requirements. For example, some tasks like semantic segmentation, they rely on low-level features like textures and edges, while others require high-level features like 3D scene understanding. So ignoring these differences between the task requirements can lead to suboptimal outcome. Just like treating all the plants the same would lead to poor growth for some. So in this presentation, I would be focusing on my research, which is titled, the paper which is titled on giving each task what it needs, leveraging structured sparsity for tailored multitask learning. This work focuses on improving the performance of multitask learning models by customizing the sharing between each task. Multitask learning is about training one model to handle multiple tasks. The underlying theory is that the tasks help each other to learn better. However, there's a challenge. Tasks can negatively impact each other through something called as negative information transfer. This can be because of oversharing or undersharing of information. Now, what do I mean by that? As you see in the figure is basically showing a hard parameter sharing setting, or an architecture with hard parameter sharing, where I'm forcing that the high level features from the shared backbone are fed to the task decoders. So what I'm doing is I'm just feeding the same information to all the tasks. And some tasks may need low level features while some may need more abstract high level features. So in this case, there's the disadvantage of negative information transfer, which negatively impacts the performance as well. Our approach solves this problem by refining the feature selection for each task. By tailoring the multitask model to meet the specific needs of the task, we can optimize the performance across all the tasks. We propose a two-step approach. In the first step, we perform single task learning with structured sparsity, which help to identify the most relevant layers of each task. In the second step, we use this information to create a tailored multitask architecture where each task only gets the feature it truly needs. Here, we show the performance analysis on the NYU dataset for 4 tasks and for 2 task combination, one with 4 tasks or like all the tasks and one with 3 tasks. The results demonstrate how the proposed layer optimized multitask models, which I've mentioned here as LOMT models, improved performance metrics like the IOU and the mean absolute error by tailoring the network to each task specific needs. The performance of the proposed LOMT models is highlighted in yellow box in the figure. To conclude, the LOMT models are effective because they optimize the layers for each task using structured sparsity. This leads to better task-specific performance and balanced learning. However, there are limitations to this work. Our method requires a two-step approach and also a careful tuning of the sparsity parameter, or I should say the strength of sparsity, that is lambda. This is just a brief overview. For more details, please take a look at the paper. If you're attending the ECCV workshop on computational aspects of deep learning, feel free to stop for a full presentation and discussion. Thank you so much.